Civilization has always strived to build at its edges. And the further from everything it builds, the more extraordinary the story becomes. In today's video, we talk about 15 such mega projects that were built in places that had no business having them. From jungles to mountain ranges, and from open ocean to desert plateaus. These mega projects defied the odds and set new limits for what's possible when the latest technology meets modern vision. Stay with us as we bring you the most remote mega projects ever built across the world. In the mid-1960s, British Columbia decided to build the largest earth-filled dam in North America in a stretch of the Rocky Mountains where there was, in practical terms, nothing. No town nearby, no road capable of handling industrial freight, no workforce within reasonable reach, just the Columbia River cutting through mountain wilderness and the hydro potential that represented. Before a single cubic meter of earth could be moved for Mica Dam itself, BC Hydro had to build the means to get there. A 130-kilometer access road was carved through the Rocky Mountain terrain from Revelstoke to the dam site, an undertaking that in other contexts would have been a significant infrastructure project on its own. The road had to be engineered to handle the continuous heavy traffic of a major construction operation through a mountain environment that included steep grades, river crossings, avalanche zones, and winters that tested the limits of what equipment could operate through. The workforce that built Mica lived on site for the duration. A construction camp was established near the dam that housed thousands of workers through multiple Canadian winters, with temperatures dropping well below -30°C for extended periods. Supply convoys kept the camp stocked with everything from concrete aggregate to food, running that 130-kilometer road through conditions that regularly made it dangerous. Workers rotated on schedules designed around the psychological reality of extended isolation in a mountain camp with no nearby town, no casual exit, and months of winter darkness. The dam itself is a massive earth and rock-fill structure, 244 meters high and nearly a kilometer wide at its crest. Building it required moving and placing tens of millions of cubic meters of carefully graded fill material in a precise sequence with different zones of material type, creating the internal structure that allows an earth dam to hold back the volume of water Mica was designed to contain. The reservoir it created, Kinbasket Lake, stretches over 200 kilometers up the Columbia River Valley, one of the largest reservoirs in Canada. The Columbia River's behavior dictated the construction sequence in the same way rivers always do on dam projects, managing river diversion, controlling flow through the partially complete structure during high water periods, and timing the closure of the dam to coincide with manageable river conditions required years of planning and precise execution in a mountain environment where the river does not behave predictably. Mica Dam was completed in 1973 after roughly 8 years of construction. Its generating capacity has been expanded over the decades since and now stands at 1,805 megawatts. It remains one of the largest hydroelectric facilities in British Columbia and a cornerstone of the provincial grid. The access road built to construct it eventually became the route that opened the Columbia River Valley to permanent settlement further north, a consequence of the project that its planners anticipated and that transformed the region in ways that outlasted the construction itself. The Yucatan Peninsula looks accessible on a map. It has cities, coastline, and tourist infrastructure. But strip away Cancun and the resort corridor, and what remains is a vast limestone jungle, the second largest tropical forest in the Americas, with almost no heavy infrastructure connecting its interior, towns separated by hours of dirt road, communities that have existed largely outside the modern economy for generations, and beneath it all, a hidden world of cenotes, caves, and underground water systems that nobody had fully mapped. And this is where Mexico decided to build one of the biggest rail systems in the world. Tren Maya had to be built despite everything that the region threw back. While this wasn't remote in the way a Siberian tundra is remote, it was remote in a more complicated way. Inhabited, ancient, and fundamentally hostile to the kind of industrial-scale construction that was about to arrive. Getting equipment into the jungle interior meant building access routes before the actual project could begin. The Yucatan has no major rivers suitable for freight. Roads capable of handling construction loads either didn't exist or had to be carved from scratch. In the early phases, machinery was moving through terrain that actively resisted movement. Dense canopy, soft limestone ground that shifted unpredictably, and a wet season that turned access routes into mud within hours. Then the ground opened up. As crews pushed deeper into the jungle, they began hitting voids beneath the surface. Caverns, cenotes, underground passages that gave no warning from above. In some stretches near the Mayan archaeological zone around Campeche, drilling equipment broke through into spaces large enough to drive a truck through. Entire sections of the route had to be redesigned. In the most unstable areas, the track was elevated on raised structures above the ground rather than laid through it. The only way to guarantee it wouldn't eventually sink into what lay below. Keeping thousands of workers operational in those conditions was its own battle. Extreme humidity, venomous wildlife, heat peaking well above 40 degrees Celsius in the dry season. And then the jungle started giving up its secrets. As construction cut through the interior, it kept finding things. Thousands of Mayan artifacts surfaced along the route. Structures, ceramics, burial sites that had sat undisturbed for centuries. Work halted repeatedly to allow excavations. By the time the project was complete, over 30,000 archaeological pieces had been recovered, turning parts of the build into an accidental dig site at industrial scale. The opposition never quieted. Scientists, indigenous communities, and conservation groups argued that a railway cutting through the jungle would fragment critical ecosystems, threaten the underground water table, and cause damage that couldn't be undone. Legal injunctions ran parallel to construction for years. The finished railway stretches 1,554 kilometers, making it the longest passenger line in Mexico and one of the longest in Latin America. It connects 5 states, passes through or near dozens of Mayan sites, and links communities that previously had no rail connection to the rest of the country. At peak construction, over 17,000 workers were active across simultaneous build fronts. The total cost exceeded $20 billion. Whether it was worth it depends entirely on who you ask. For the communities it connects, many of them poor and economically isolated for generations, it's a lifeline. For the ecologists and archaeologists who watched it go up, it's a wound cut through something irreplaceable. The jungle is already growing back around the tracks in places. But next up, we have an even more extreme railway megaproject in China, one that was built at an altitude where the human body may struggle to function properly. The Qinghai-Tibet Railway is built at 5,072 meters above sea level, making it the highest railway ever built, and it runs through some of the world's harshest terrain for over 960 kilometers. The railway connects Xining in Qinghai province to Lhasa, the capital of Tibet, crossing the Tibetan Plateau, a landmass so high and so vast, it's known as the roof of the world. Before this line existed, reaching Lhasa by land meant days of grueling road travel through terrain that regularly closed in winter. Tibet was effectively cut off from the rest of China in any practical modern sense. The railway was built to change that permanently. The distance is 1,956 kilometers in total. The section from Golmud to Lhasa, the stretch that broke every record, took 5 years to complete and required solutions that had never been attempted at this scale anywhere on Earth. Half the route runs over permafrost, not frozen ground that thaws in spring, but deep, ancient permafrost that had been stable for thousands of years until construction equipment arrived and began generating heat. Permafrost melts unevenly. It subsides in patches. A railway track laid directly onto it would warp, buckle, and eventually become unusable within years. Chinese engineers solved this by essentially refrigerating the ground beneath the tracks. Thermosiphon devices were driven into the earth along the most vulnerable stretches, passively drawing heat out of the ground and keeping the permafrost frozen even as the climate around it warmed. It was an engineering approach borrowed from pipeline construction in Alaska and Canada, scaled up to a degree nobody had attempted before. Over 160 bridges and tunnels were built along the route. The Fenghuoshan Tunnel, at 4,905 meters above sea level, was the highest railway tunnel in the world at the time of construction. Workers inside it were operating at altitudes where oxygen levels are roughly 60% of what they are at sea level. China built oxygen-enriched work camps along the line, pumping pressurized air into sleeping quarters and work tents to keep crews functional. Mobile medical units followed construction teams across the plateau. Over 100,000 workers were deployed at peak. The project recorded remarkably few altitude-related fatalities given the conditions, a result of the medical infrastructure built specifically around the workforce. The trains themselves had to be redesigned. Standard rolling stock can't function at that altitude. The carriages used on the Qinghai-Tibet line are pressurized like aircraft cabins, with individual oxygen supplies at each seat. The locomotives were modified to operate in thin air, where combustion and cooling systems behave differently than at sea level. The line opened in 2006, on schedule, after 5 years of construction. It cost approximately $4.2 billion. It carries passengers and freight across a plateau that was, for most of human history, considered simply impassable. The controversy around it has never fully settled. Tibet's political status means the railway carries weight beyond engineering. Critics argue it accelerated Han Chinese migration into the region and deepened Beijing's grip on a territory with a contested history. Supporters point to the economic development it unlocked and the hundreds of thousands of Tibetans who now have direct rail access to the rest of the country. Both things are true, and neither cancels the other out. What isn't contested is what was built: a railway across the roof of the world, through frozen ground, at altitudes that kill, completed on time, and still running today. From these extraordinary rail projects, we move to some of the most extraordinary dams in most isolated locations. In 2011, Brazil broke ground on a dam in the middle of the Amazon. What followed was 10 years of jungle, floods, and one of the most bitterly contested construction projects on Earth. Belo Monte is the third largest hydroelectric dam ever built. It sits deep in the Brazilian Amazon on the Xingu River, roughly 500 kilometers from the nearest major city. Building it meant moving more earth than was excavated for the Panama Canal, in a jungle that receives over 2 meters of rainfall per year, and in a region with no existing heavy infrastructure. Getting materials to the site required building that infrastructure first. A dedicated port was constructed on the Xingu River to receive heavy equipment shipped in by barge. Roads were cut through the jungle to connect the construction zone to supply lines. At peak, the site was operating like a small city, housing over 30,000 workers with their own hospitals, schools, and supply chains, running continuously to keep construction moving. The Xingu is not a simple river to engineer around. Its flow varies enormously between wet and dry seasons, which dictated the entire construction sequence. Work had to be staged around the river's behavior, with different sections of the dam built during windows when water levels and currents allowed it. Cofferdams, temporary structures used to hold back water while permanent works are built behind them, had to be erected and dismantled in sync with seasonal cycles. Missing a window meant waiting an entire year. The scale of what was built is staggering. The Belo Monte complex includes 2 powerhouses, dozens of kilometers of canals, multiple dikes, and a main dam structure that required moving 240 million cubic meters of earth and rock during construction. The reservoir created by the project covers nearly 500 square kilometers. The installed generating capacity is 11,233 megawatts, enough to power the equivalent of 60 million Brazilian homes at full output. Full output, however, is the problem. The Xingu's flow drops dramatically in the dry season, and Belo Monte was designed without large water storage reservoirs, meaning its actual average output runs well below its theoretical maximum. Critics called this a fundamental design flaw built into the project from the beginning. The dam's operators and the Brazilian government argued the numbers still justified the investment when integrated across the full year. While it was billed as a net positive for the country, the construction began with a significant human cost. Approximately 40,000 people were displaced by the project, many of them indigenous communities whose lives along the Xingu had remained largely unchanged for centuries. The flooding altered fish migration patterns the river communities depended on. Environmental groups, indigenous rights organizations, and figures including the filmmaker James Cameron flew to the region to oppose the project publicly. Legal battles ran for years. Construction continued regardless. Belo Monte was completed in stages between 2016 and 2019. Its final cost reached approximately $18.5 billion, nearly double the original estimate. It now supplies a significant share of Brazil's national grid, a grid that was experiencing serious shortages and blackouts in the years before the dam came online. Whether the Amazon paid too high a price for that power is a question Brazil is still working through. The river keeps moving. The dam isn't going anywhere. Laos is one of the most landlocked and least industrialized countries in Southeast Asia. It has no coastline, limited road infrastructure across most of its interior, and a national grid that for most of its population has historically meant unreliable power, or none at all. Theun 2 was built to change that, not by powering Laos, but by selling electricity to Thailand and using the revenue to fund the country's development from the outside in. The dam sits on the Theun River on the Nakai Plateau, a remote highland region in central Laos, roughly 250 kilometers east of the capital Vientiane. Before construction began, the plateau was accessible by a single unpaved road that became impassable in the wet season. There was no heavy freight route, no port, no existing industrial infrastructure of any kind. Everything the project needed had to be brought in, and in many cases the means of bringing it in had to be built first. A new road was constructed from the Thai border to the project site, capable of handling the convoys of heavy equipment and materials that would sustain years of continuous construction. A temporary airstrip was built near the site for personnel and priority freight. The construction workforce at peak reached around 7,000 people, housed in a purpose-built camp on the plateau that operated its own water treatment, medical facilities, and power supply independently of anything the surrounding region could provide. The Nakai Plateau sits at the edge of one of the last intact lowland forest ecosystems in Southeast Asia. The reservoir created by the dam flooded approximately 450 square kilometers of that forest, displacing around 6,200 villagers from communities that had lived on the plateau for generations. The resettlement program that accompanied the project was among the most extensively documented in the history of large dam construction, designed under World Bank oversight with commitments to land replacement, livelihood support, and long-term monitoring. Whether those commitments were fully honored remains a contested point between the project's developers and the communities affected. The environmental conditions during construction were brutal in the way that jungle environments always are. Humidity, heat, monsoon rains that turned access routes into rivers, and a wet season that effectively shut down certain phases of work for months at a time. The dam itself, a concrete-faced rock-fill structure, required continuous supply of aggregate and fill material from quarries established near the site, with haulage roads maintained through conditions that degraded them almost as fast as they could be repaired. Theun 2 began generating power in 2010. Its installed capacity is 1,070 megawatts, with the vast majority of output exported directly to Thailand under a long-term power purchase agreement. The revenue flows to the Lao government and has funded infrastructure, education, and health programs across the country. It became a reference case in international development circles for the model of using natural resource exploitation to finance national development, and a cautionary example for those who argue the communities displaced by such projects rarely see proportionate benefit. The dam generates power continuously. The plateau it flooded does not come back. The Yamal Peninsula sits at the top of Russia, where the Arctic Ocean meets Siberia. In winter, temperatures drop to -50 degrees Celsius. The ground is frozen solid year-round. There are no roads in or out. There is no port. There is, or was, almost nothing there at all. Russia built one of the largest liquefied natural gas plants on Earth on it anyway. The Yamal LNG project was designed to extract natural gas from fields beneath the peninsula, cool it to -162 degrees Celsius to liquefy it, and ship it out through Arctic waters to markets in Europe and Asia. The scale of what that required, in a place that extreme, defines what makes Yamal different from almost every other energy project ever attempted. Everything had to be brought in by sea, and only during the narrow Arctic summer window when ice conditions allowed. A dedicated port was built from scratch at Sabeta, on the eastern shore of the peninsula, dredged out of shallow Arctic waters and constructed to handle the kind of cargo volumes that would supply a continuous industrial operation in one of the most inaccessible places on the planet. In winter, when the port froze over, specially built ice-breaking LNG tankers kept the supply lines moving, vessels designed specifically for this project that can operate independently in ice over 2 meters thick. The workforce at peak numbered around 30,000 people, living in an Arctic industrial camp that functioned as a self-contained city. Flights were the only way in or out for most of the year. Workers rotated on schedules designed around the psychological and physical limits of sustained Arctic exposure, with rest periods mandatory and medical infrastructure built directly into the camp, in temperatures where exposed skin freezes in minutes. Outdoor construction work required specially engineered equipment, heated suits, and strict time limits on surface exposure. The permafrost presented the same fundamental problem it creates for every structure in the Arctic. Buildings and industrial equipment placed on frozen ground generate heat that melts the permafrost beneath them, causing subsidence and structural failure. Every structure at Yamal was built on thermally insulated piles driven deep into the ground, with air gaps beneath buildings to prevent heat transfer. The same principle applied to pipelines, processing equipment, and the port infrastructure. The 3 LNG processing trains at Yamal, the core of the plant, were not built on site. They were constructed in modules in shipyards in China, South Korea, and Europe, then transported on heavy lift vessels through Arctic waters and assembled at Sabeta. Moving prefabricated industrial modules the size of apartment blocks across thousands of kilometers of ocean, through ice, and landing them precisely onto prepared foundations in an Arctic port was a logistical sequence that took years of planning and had no precedent at this scale. Yamal LNG produced its first cargo in 2017. By 2019, all 3 processing trains were operational. The total investment reached approximately $27 billion. It now supplies LNG to markets across Europe and Asia year-round, with the ice-breaking tanker fleet keeping shipments moving even through the depths of the Arctic winter. The project sits inside one of the most geopolitically sensitive energy corridors in the world, and the sanctions imposed on Russia following the invasion of Ukraine in 2022 have complicated its international partnerships significantly. The technology and financing that made Yamal possible came partly from Western partners who have since withdrawn. A planned expansion, Arctic LNG-2, has stalled as a result. What was built, however, keeps running. The Arctic doesn't pause for politics. Next up, we have 2 of China's craziest megabridges, built hundreds of kilometers away from any civilization. China opens a new bridge somewhere almost every week. This one is different. The Huajiang Grand Canyon Bridge spans a gorge in Guizhou province so deep that clouds form below the deck. When it opened in 2024, it became the highest bridge in the world, with a deck sitting 625 meters above the Beipan River. To put that in perspective, you could stack the Eiffel Tower on top of itself 3 times and still not reach the roadway. Guizhou is one of China's poorest and most mountainous provinces. The terrain is a maze of karst peaks, sudden gorges, and valleys that made building any kind of modern transport network across the region extraordinarily difficult. Communities on opposite sides of these canyons were separated not by distance on a map, but by hours of winding mountain road. The Huajiang Bridge was built to collapse that separation permanently. The gorge itself dictated everything. At 625 meters deep and over a kilometer wide at the crossing point, there was no conventional way to string a bridge across it. The foundations had to be anchored into near-vertical canyon walls on both sides, with construction teams working on cliff faces using equipment suspended over drops that left no margin for error. Drilling into the rock to seat the anchor points required precision at heights where standard construction methods simply don't apply. The main span stretches 1,420 meters between towers. Building the towers themselves meant working at different elevations simultaneously, with crews on the canyon rim above and others operating hundreds of meters below on platforms fixed to the cliff face. Materials and equipment moved by cable systems strung across the gorge before the bridge structure existed to carry anything. Getting a single load of concrete to the right position could take the better part of a working day. Wind was a constant variable. At that elevation, in an open canyon of that scale, gusts are unpredictable and strong enough to affect the movement of heavy loads on cables. Construction schedules were built around weather windows, and crews learned to read conditions in a gorge that generates its own microclimate. The bridge carries a 6-lane expressway and cuts the travel time between communities on either side of the canyon from around 4 hours to approximately 3 minutes. It is part of a broader infrastructure push across Guizhou that has seen dozens of major bridges built over the past 2 decades, transforming a province that was once considered too difficult to connect into one of the most bridged regions on Earth. Guizhou now hosts more than half of the world's highest bridges. The Huajiang is the tallest of them all, and by the time another country attempts something at this scale, China will likely have built several more. Building a bridge across open seas is hard. Building one across one of the busiest shipping lanes in the world, in Typhoon territory, with 3 different governments involved, is something else entirely. The Kong-Zhuhai-Macau Bridge stretches 55 kilometers across the Pearl River Delta, making it the longest sea crossing ever built. It connects 3 of the most economically significant cities in southern China, a region that collectively generates more GDP than many mid-sized countries. Before it existed, the road journey between Hong Kong and Zhuhai took 3 to 4 hours. The bridge does it in 30 minutes. The Pearl River Delta is not open water. It is one of the most congested maritime corridors on Earth, with thousands of cargo ships, tankers, and ferries moving through it every day. Running a bridge across it would have blocked shipping lanes that the regional economy depends on. The solution was to take the bridge underwater for a section in the middle, dropping into a 6.7-kilometer undersea tunnel that allows vessels to pass over the top while traffic continues below. The transition points between bridge and tunnel required the construction of 2 artificial islands, each roughly the size of several city blocks, built from scratch in open water to house the tunnel portals. Those islands took about 3 years to build. Steel cylinders, each weighing hundreds of tons, were driven into the seabed and filled with sand and concrete to form the foundations. The precision required to position them correctly in tidal currents and shipping traffic, without disrupting either, pushed construction teams to the edge of what marine engineering had done before. The main bridge structure had to be built with typhoon loads factored into every joint and cable. The Pearl River Delta sits in an active typhoon corridor, and the bridge was designed to withstand winds that would shut down most infrastructure in the region. Seismic activity added another layer, with the structure engineered to flex rather than resist during ground movement. In total, over 400,000 tons of steel went into the crossing, enough to build 60 Eiffel Towers. The project employed around 14,000 workers at peak, many of them living on accommodation vessels anchored near the work site. The total cost reached approximately $18.8 billion. It opened in 2018, after 9 years of construction. The politics of who can actually use it added a layer of complexity the engineering couldn't solve. Due to different vehicle registration and permit systems across Hong Kong, Macau, and mainland China, access to the bridge is restricted. Most travelers cross via shuttle buses rather than private vehicles, which limited the traffic volumes that were originally projected. The bridge carries far fewer vehicles per day than its capacity allows, a gap between engineering ambition and administrative reality that still draws criticism. What it achieved structurally remains largely without precedent. A 55-kilometer crossing, part bridge, part tunnel, with artificial islands built in open water across one of the most active shipping lanes on Earth. India has been building a railway through the Himalayas for over 2 decades. It is not finished yet. The Udhampur-Srinagar-Baramulla rail link was launched in 1997 with the goal of connecting the Kashmir Valley to the Indian rail network for the first time. Kashmir sits in the northwestern Himalayas, bordered by Pakistan, China, and some of the most geologically unstable terrain on Earth. Before this project, the valley was accessible by road through mountain passes that closed for months every winter, leaving it effectively cut off from the rest of the country on a seasonal basis. The railway was supposed to take a few years. The geology had other plans. The central section of the line between Katra and Banihal passes through the Greater Himalayas, a stretch of mountain terrain so fractured, so prone to landslides, avalanches, and seismic movement that construction teams spent years simply trying to understand what they were building into before they could begin. Bore surveys revealed rock formations that changed composition within meters, with hard granite giving way to soft shale unpredictably. Tunnels that appeared straightforward on paper collapsed during drilling. Methods had to be abandoned and redesigned repeatedly. The numbers that came out of this section are genuinely difficult to process. The Banihal-Kazigun Tunnel alone stretches 11.2 kilometers. The Pir Panjal Tunnel runs 11.2 kilometers through a mountain range that experiences regular seismic activity, but neither of those is the defining structure of the project. That distinction belongs to the Chenab Bridge, which when completed became the highest railway bridge in the world, with its arch rising 359 meters above the Chenab River, taller than the Eiffel Tower. Building the Chenab Bridge arch required constructing it from both sides of a deep river gorge simultaneously, with the two halves meeting in the middle. The arch had to be supported by a cable stay system during construction, with temporary stays holding the structure in position until the two sides connected and the arch became self-supporting. Wind speeds in the gorge regularly exceeded the limits for safe crane operation, shutting work down for days at a time. The arch is designed to withstand winds of 266 kilometers per hour and a full seismic event. Workers on this project weren't rotating through a purpose-built camp near a city. They were living in temporary settlements inside one of the world's most active conflict zones, in terrain that avalanched without warning, at altitudes where winters are brutal and supply lines thin. The project has seen extended stoppages, security incidents, and cost revisions that have taken the total bill from an original estimate of around $2 billion to over $35 billion across the full line. Sections of the railway have opened progressively. The full connection to Srinagar is expected to bring a rail link to a valley that has waited nearly 30 years for one. When the final spike goes in, it will be one of the most expensive kilometers of railway ever built, through terrain that fought back at every stage. The Atacama Desert in northern Chile is one of the driest places on Earth. In some parts of it, there is no recorded rainfall in human history. The air is so thin and so dry that it is almost entirely free of water vapor, which makes it useless for agriculture, hostile to human life, and perfect for looking at the universe. The Atacama Large Millimeter Array, ALMA, sits at 5,050 meters above sea level on the Chajnantor Plateau. It is the most complex ground-based telescope ever built, an array of 66 high-precision antennas that function together as a single instrument capable of observing the cold universe, the clouds of gas and dust where stars and planets form, with a clarity no telescope before it could match. Getting those 66 antennas to the plateau required building a road capable of handling vehicles carrying loads up to 115 tons, up a mountain, to an altitude where construction workers needed supplemental oxygen just to function. The antennas themselves, each one a precisely engineered dish weighing over 100 tons, were transported individually up that road on custom-built antenna transporters, vehicles with 28 wheels and their own active suspension systems designed to keep the dish level to within fractions of a millimeter, regardless of the road surface beneath them. The construction workforce operated on strict rotation cycles because sustained exposure at that altitude causes lasting physiological damage. Workers would spend a limited number of days at the high site, then descend to a support facility at 2,900 meters to recover before returning. Even with those protocols, altitude sickness was a constant presence. Headaches, fatigue, and impaired coordination were routine. The more serious risk, pulmonary edema, the flooding of the lungs with fluid, was a medical emergency that the site's health team was permanently prepared for. The antennas had to be positioned and repositioned across the plateau in different configurations depending on what astronomers wanted to observe, which is why the transporters were built to move them rather than fix them permanently. Coordinating the movement of 100-ton precision instruments across high-altitude terrain without damaging equipment that cost tens of millions of dollars per unit, was an operational challenge that continued long after construction was complete. The electronics at the heart of ALMA operate at temperatures close to absolute zero, cooled by cryogenic systems that have to function reliably in an environment that is already brutally cold by any human standard. The signal processing required to combine data from 66 separate antennas into a single coherent image is handled by a correlator. At the time of its construction, the most powerful scientific computer ever built for a single instrument. ALMA took over a decade to construct and reached full operation in 2013. The total cost was around $1.4 billion, shared across a partnership of North American, European, and East Asian institutions. Since opening, it has produced observations that have reshaped understanding of planetary formation, galaxy evolution, and the molecular chemistry of deep space. In 2019, the data it contributed helped produce the first direct image of a black hole's event horizon. At 5,050 meters, in a desert that doesn't rain, the clearest window humanity has into the cold universe sits pointed at the sky. Norway has a geography problem. Its western coastline is one of the most fragmented on Earth, cut through by fjords that make direct road travel between coastal communities functionally impossible without ferries. The ferry crossings work, but they are slow, weather-dependent, and a bottleneck for a modern economy that needs reliable, year-round connections. The Rogfast tunnel is Norway's answer to one of those crossings. When complete, it will be the longest and deepest road tunnel in the world, running 26.7 kilometers beneath the Boknafjord, reaching a depth of 392 meters below sea level at its lowest point. It will replace a ferry crossing that currently takes about 25 minutes, but requires travelers to stop, board, wait, and disembark, adding time and unpredictability to every journey. Drilling a tunnel 26.7 kilometers through subsea rock at that depth is not a straightforward engineering exercise. The rock beneath the Boknafjord is hard but fractured in places, with zones of weakness that pressurized water exploits. At 392 meters below sea level, the water pressure against the tunnel walls is immense. Breakthrough points, where the drill breaks into a weakness in the rock, can result in water ingress at volumes that halt construction entirely until grouting operations seal the fracture. Managing water has been one of the dominant technical challenges throughout the build. The tunnel is being bored by tunnel boring machines from multiple faces simultaneously, with crews working from both ends and from an intermediate access point to accelerate progress. The spoil, the rock excavated from the tunnel, has to be transported out continuously, while fresh concrete lining segments and construction equipment move in the opposite direction, a logistical choreography that runs around the clock. The tunnel descends steeply from both portals to reach its deepest point beneath the fjord, which creates a long downhill gradient for vehicles entering from either side. Managing ventilation in a tunnel that long and that deep, ensuring that vehicle exhaust and emergency smoke can be cleared effectively, required a ventilation system of a scale that pushes the boundaries of what has been built into a road tunnel before. Emergency laybys, cross passages, and evacuation routes had to be engineered into the tunnel at regular intervals throughout its length. Construction began in 2018, and the project has faced delays and cost increases that have pushed the opening date and the budget beyond original projections. The current cost estimate sits at approximately 43 billion Norwegian krone, roughly $4 billion. When it opens, it will form part of the E39 Coastal Highway project, Norway's broader ambition to create a continuous ferry-free road connection along its entire western coast. A project so large and so expensive, it is sometimes described as Norway's most ambitious infrastructure undertaking ever. The Boknafjord crossing is one piece of that. When vehicles drive through Rogfast, they will be traveling deeper below sea level than almost any road on Earth, through a tunnel that took the better part of a decade to bore, beneath a fjord that gave no ground easily. The Alps have divided Europe since before Europe was a concept. Every trade route, every military campaign, every attempt to move goods between northern and southern Europe has had to reckon with them. The Gotthard Pass, in central Switzerland, has been one of the primary crossing points for centuries. In winter, it closes. At all times, it is slow. The Gotthard base tunnel was built to go through the Alps rather than over them. At 57.1 kilometers, it is the longest railway tunnel in the world. It runs in a straight line beneath the Swiss Alps at a near-flat gradient, connecting Erstfeld in the north to Bodio in the south, cutting the rail journey between Zurich and Milan by nearly an hour, and allowing freight trains that previously had to crawl over mountain passes to move at full speed through the heart of the continent. The project took 17 years to build and required excavating approximately 28 million tons of rock. The tunneling was done by a combination of tunnel boring machines and conventional drill and blast methods, with different techniques applied depending on the rock conditions encountered at different depths. The geology beneath the Alps is not uniform. Crews moved through granite, through gneiss, through unexpected zones of fractured rock and water under pressure, each transition requiring a reassessment of the drilling approach and pace. At its deepest point, the tunnel sits 2,300 meters beneath the mountain surface above it. The rock at that depth is under enormous pressure and generates significant heat. Temperatures inside the unventilated tunnel during construction reached 46 degrees Celsius. Workers were operating in conditions that required continuous cooling systems just to make the environment survivable, let alone productive. 4 main access tunnels were drilled from the surface to allow construction to proceed from multiple intermediate points simultaneously, rather than purely from the 2 ends. This was essential to completing the project within any realistic time frame. Even with those access points, coordinating construction across multiple headings, managing the spoil removal, the concrete lining installation, and the installation of railway systems while tunneling was still ongoing in adjacent sections, was a project management challenge on a scale that had no direct precedent. Around 2,600 workers were on site at peak, drawn from across Europe. The project recorded 9 fatalities over its construction period, a number that project managers considered a marker of the safety systems in place given the scale and duration of the work. The total cost reached approximately 12.2 billion Swiss francs, making it one of the most expensive infrastructure projects in European history. The tunnel opened in June 2016 and entered full commercial operation shortly after. It now carries both high-speed passenger trains and heavy freight, moving goods between northern and southern Europe through the mountain rather than around or over it. The Alpine crossing that shaped trade routes for centuries now takes trains 17 minutes to complete at 200 kilometers per hour. The Massif Central Plateau in southern France drops without warning into the Tarn River Valley, a gorge several hundred meters deep that cuts directly across the main route between Paris and the Mediterranean. For decades, every vehicle making that journey had to descend into the valley and climb back out, or queue through the town of Millau below, which turned summer holiday traffic into a gridlock that became a national frustration. France decided the solution was to go over it entirely. The Millau Viaduct, completed in 2004, is the tallest bridge in the world. Its highest mast reaches 343 meters, taller than the Eiffel Tower. The roadway itself sits 270 meters above the valley floor at its highest point. It carries the A75 motorway across a 2.46-kilometer span on 7 concrete piers, each one sunk into valley ground and rising to heights that put the deck above the clouds on overcast mornings. The engineering problem wasn't simply height. It was achieving that height while maintaining the structural precision a motorway demands. The deck had to be level, smooth, and geometrically consistent across its full length, despite being assembled in sections pushed out from both sides of the valley on temporary supports. The technique used was incremental launching, where sections of the deck were built on the valley rim and then hydraulically pushed forward over the piers in stages. At certain points during construction, sections of deck were cantilevering over 600 meters into open air with nothing beneath them but valley floor. Wind in the Tarn Gorge is constant and directional, channeled by the valley walls into forces that the bridge had to be designed to absorb rather than resist. The deck incorporates a slight curvature in both the horizontal and vertical plane, which improves aerodynamic stability and prevents the resonance effects that have caused structural failures in long-span bridges elsewhere. The The 7 piers are not perfectly vertical either. Each one leans very slightly inward at the top to account for the curvature of the earth across the bridge's length, a detail that is invisible to anyone crossing it, but essential to the geometry holding together. Construction employed around 2,000 workers over 3 years. The project finished on schedule and within its €394 million budget, which for a structure of this scale and ambition is almost as remarkable as the bridge itself. It opened in December 2004 and has since become one of the most visited structures in France, drawing people who come not to cross it, but simply to look at it. Every morning when low cloud fills the Tarn Valley, drivers on the A75 cross above it on a deck that appears to float free of the ground entirely. The valley that stopped traffic for generations now takes less than a minute to cross at motorway speed. The Mojave Desert receives more sunlight per square meter than almost anywhere in the continental United States. It also has no water, no shade, summer temperatures that exceed 50 degrees Celsius, and until recently, very little reason for anyone to be there in large numbers. Ivanpah changed that. The Ivanpah Solar electric generating system sits on 14 square kilometers of desert in San Bernardino County, California, near the Nevada border. It is not a conventional solar farm. Rather than photovoltaic panels converting sunlight directly into electricity, Ivanpah uses a different approach entirely. Around 350,000 computer-controlled mirrors, called heliostats, are arranged across the desert floor in concentric arcs around 3 central towers. Each mirror tracks the sun independently throughout the day, reflecting concentrated sunlight onto boilers at the top of the towers. The heat generated produces steam, which drives turbines to generate electricity. At full output, the plant produces 392 megawatts, enough to power approximately 140,000 homes. Building 350,000 individual mirrors across 14 square kilometers of desert, each one requiring its own foundation, motor system, and connection to a central control network, was a construction and logistics challenge that dwarfed most comparable energy projects. Over 100,000 tons of steel went into the heliostat structures alone. The 3 towers, each rising over 130 meters from the desert floor, had to be constructed in an environment where summer working conditions pushed crews to their physical limits, and where the concentration of reflected sunlight created hazard zones around the towers that required strict operational protocols during construction. Water, essential for the steam cycle and for cleaning the mirrors, had to be managed carefully in a desert with no natural water source nearby. A water supply infrastructure was built as part of the project, with conservation systems designed to minimize consumption in a region where water is a resource with its own political and environmental weight. The project faced sustained opposition from environmental groups, which created a specific tension. A solar plant built to reduce carbon emissions was simultaneously destroying desert tortoise habitat and disrupting a fragile ecosystem that had taken centuries to establish. Thousands of tortoises were relocated during construction. Critics argued the relocation programs were inadequate. The desert doesn't recover from industrial-scale ground disturbance quickly, and the footprint of 14 square kilometers is not a small imposition on an ecosystem that functions on subtle balances. Since opening in 2013 and 2014, Ivanpah has consistently underperformed its projected output, partly because the Mojave's actual cloud cover exceeded the models used during planning, and partly because the technology, while functional, proved less efficient in real-world desert conditions than its developers had projected. The plant has required natural gas supplements to maintain steam pressure on lower sunlight days, which drew pointed criticism given that it was built as a zero-emission facility. The investment totaled approximately $2.2 billion. It remains the largest concentrated solar thermal plant in the world, a record it has held since opening, and a demonstration that the technology works at scale, even if the economics have proven more complicated than the original projections suggested. There is nothing at Dogger Bank. That is precisely the point. Dogger Bank is a submerged sandbank in the North Sea, sitting between 125 and 290 kilometers off the northeast coast of England. It is shallow enough by North Sea standards, between 18 and 63 meters deep, but it is open ocean, exposed to North Sea weather. with no land nearby, no shelter, and conditions that shut down marine operations for significant portions of the year. When the decision was made to build the world's largest offshore wind farm there, the nearest question wasn't how, it was why anyone would attempt it at all. The answer was wind. Dogger Bank sits in one of the most consistently windy stretches of ocean in the world, where prevailing Atlantic weather systems produce wind speeds and consistency that onshore sites and nearshore installations can't match. The further offshore, the stronger and steadier the wind. Dogger Bank is far enough offshore that its turbines operate at capacity factors that make the economics, despite the staggering logistical difficulty, work. The wind farm is being built in 3 phases, designated A, B, and C, each one a separately consented and financed project. Combined, they will install 277 turbines across an area of approximately 516 square kilometers of open ocean. Each turbine stands on a monopile foundation driven into the seabed, with the nacelle sitting over 150 meters above the water surface. The turbines being installed are among the largest ever built, with rotor diameters exceeding 260 meters. A single rotation of one blade generates enough electricity to power a home for 2 days. Installing foundations in open ocean 130 kilometers from shore required a fleet of specialized vessels that don't exist in large numbers anywhere in the world. Heavy lift vessels, installation ships, crew transfer vessels, and floating accommodation units had to be coordinated in a logistics chain that ran continuously during weather windows, with any delay cascading through a schedule that had no buffer to absorb lost days easily. The monopile foundations, each weighing thousands of tons, were manufactured on shore, transported by sea, and driven into the seabed by hydraulic hammers mounted on installation vessels that had to hold precise position in open ocean swells. The cable infrastructure required to bring power from 130 kilometers offshore to the onshore grid is itself a significant engineering undertaking. High-voltage direct current cables run along the seabed to converter stations on shore, where the power is converted and fed into the national grid. The cable-laying vessels that installed them worked in sea conditions that routinely suspended operations, adding months to the installation schedule. When all 3 phases are complete, Dogger Bank will have a total installed capacity of 3.6 gigawatts, enough to power 6 million British homes. Phase A began generating power in 2023. Phases B and C are progressing toward completion in the mid-2020s. The total investment across all 3 phases is expected to exceed $9 billion. Every turbine at Dogger Bank sits where there is nothing else. No ground to stand on, no shelter from the weather, no infrastructure that existed before the project created it. In the entire history of construction, very few things have been built in conditions this remote, at this scale, with this little to start from. That is what puts it at number 1. These were some of the biggest mega projects built in some of the world's most remote locations. But which one did you find the most impressive? Let us know in the comments below. Don't forget to subscribe and keep following Signum for more extraordinary tales behind the world's most impressive mega projects.